Okay. Ooh. So last video I said we were going to talk about heating and cooling curves. We actually ended up talking about phase diagrams. So this video, I'm going to talk about heating and cooling curves, I promise. Here we go. All right, let me get some better paper here. First, we need some lines. Let's just stick with white. Use white with lines. Oops. Okay. All right. Heating and cooling curves. All right. We would need some of those values that we wrote down. Specific heat of water in its solid form was what? 2.05 joules per gram degrees Celsius. Specific heat of water in its liquid form was what? 4.184 joules per gram degrees Celsius. Specific heat of water in its gaseous form was what? 2.08 joules per gram degrees Celsius. Delta H fusion, we talked about that. That was 6.02 kilojoules per mole. And delta H vap, we talked about that. I think it was 40.2 kilojoules per mole. All right. So what we will do is we will use those numbers to do some calculations, just making sure that I wrote down the numbers, correctly. All right, so let's go back here. And let's draw what a heating curve looks like, okay? And it's always nice to assume that we're talking about water because we all know about the phase change temperatures for water when it boils and when it freezes. So it's nice to do water. This is going to be a graph. This will be our y-axis. This will be our x-axis. Down here, we'll kind of have time, right? As time, actually, yes. And over here, we're going to have our temperature, okay? So, and we're going to have this temperature in degrees Celsius. And this is as we add heat, right? So as we move across, we are adding heat, okay? Well, let's say that we start at a temperature that's below freezing. Let's make that negative 20 degrees Celsius. Well, we know at that, if this is water and it's negative 20, it's going to be a solid. And we are going to add heat to that solid, and we're going to see its temperature go up, right? So right here, we have the solid present. We have ice. Once that solid gets to 0 degrees Celsius and it's water, well, what is it going to do? It's going to start to melt. All right. So right here we have the solid and the liquid. Okay. And notice that we have a flat line. Our temperature is not changing. Right? This is our phase change. We have a flat line. The temperature is not changing. Once all of that solid turns into a liquid, all of it melts, then you will see that temperature go back up, start to change. And at this point, we have a liquid phase only. All right? And when that liquid, as it's being heated, reaches 100 degrees Celsius, it will begin to boil. And what we'll see is the temperature stop changing. Okay? The temperature will stop changing. And on that line, I'm going to write liquid to gas. Okay? I've got my liquid turning into a gas. Once all of the liquid is boiled or evaporated, then we will only have a gas present and we will see its temperature increase. That's a heating curve. So a couple things to note is that wherever we have our flat lines and a constant temp, constant temp is where we also have our phase change. So what you see is during the phase change, the temperature does not change. So as you're boiling your water, it does not get any hotter. Yes, you're adding heat, and you're constantly adding heat. The heat added is overcoming intermolecular forces, not increasing the temp, right? The temp, right? If you're not aware of this, write it down. Temperature is a direct measurement of what? What are you measuring when you measure the temperature? Kinetic energy, okay? So if our temperature is not changing, then the kinetic energy is not changing. So what we're gaining here is potential energy is going up. Kinetic energy stays the same. Okay? That is what's occurring at all phase changes. We're either increasing or decreasing the potential energy, but not the kinetic energy. And we know that because the temperature is not changing. If the temperature is changing, the kinetic energy is changing. At the phase change, or I'm sorry, where you see the increase in temperature, right? At these points, let me get a different color there. At these points, right, we have increase in temp. So we have an increase in kinetic energy, okay? All right. Now, let's draw that again because it'll get too messy. I need to add more information to it. So we have a solid, we're heating it up. The solid begins to melt. We have a liquid, we're heating it up. The liquid begins to boil. We have a gas that's heating up. All right, this is your temp. This is your time. All right, solid, solid, liquid, 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 gas, gas. Now let's talk about the calculations here. Right here, in order to calculate the heat required to increase the temperature of the solid from -20 to, let's say this is water, 0, we would use the calculation Q equals mc solid delta T. Right here, where we are increasing the temperature of the liquid, right? That went from here to here, from here to here. We would say that the heat is equal to the mass of the liquid, the specific heat of the liquid, and the change in temp of the liquid. Right here, when we are increasing the temperature of the gas, we would say that the energy required to do that is equal to the mass of the gas, the specific heat of the gas, the change in temperature of the gas. During our phase changes, right here, we're going to have to use a different calculation because our temperature is not changing. So it would appear as though we were adding 0 heat if we added the same, if we use the same equation. So we cannot use Q equals mc delta T because delta T is 0. The temperature is not changing. However, we are adding heat. The equation used to determine the amount of heat is Q equals delta H fusion times the moles. All right. And for this phase change, we do Q equals delta H VAP times the number of moles. The reason for that is because the vaporization deals with the liquid to the gas phase change, and the fusion deals with the solid to the liquid phase change. You need to be mindful of units. All right, so let's do an example. Let's see. I'm going to erase that be mindful of units so that my example will fit well on my screen. Let's do an example. Okay, how much heat is required to raise the temp of 150 grams of water from -20 degrees Celsius to 120 degrees Celsius? Well, that's going to take us, if we assume that this happens at 0, this happens about 100, because this is water, and then we could say that up here was our 120. Okay, so we've got to go through all different parts of this graph. We first have to go from a solid at -20 to a solid at 0 degrees. So we have to go from a solid at -20 degrees to 0 degrees. That's a solid to a solid. We will do that by saying Q equals MC delta T. Okay, so let's calculate the energy required to get from there to there. Well, Q is equal to the mass of the water. It's 150 grams times, this is a solid, so we need the specific heat of the solid. That is 2.05. We wrote it down up above, all right? 2.05 joules per gram degrees Celsius. And we are going to go from 0 degrees Celsius to actually, we're going to end up at 0. We started it at 20, so that would be a positive 20. So what we have here is on 20 plus 20 times 2.05 times 150 equals, that is 6.15 times 10 to the third joules. All right, so that's just going to get us from here to here. We now need to melt the ice, right? We need to get from solid to only liquid, all right? So we've got to take our 0 degrees Celsius solid to a 0 degrees Celsius liquid. And that's going to be Q equals delta H fusion times the number of moles. All right? Well, we've got 150 grams of H2O. There's 18.02 grams in every 1 mole. 150 divided by 18.02 equals, that's 8.32 moles of H2O. So Q is equal to, let's see, the fusion is 6.02 kilojoules per mole times the 8.32 moles. 6.02 times 8.32 equals, oh my goodness, that's 50.1 kilojoules. However, this answer is in joules, so let's go ahead and take our 50.1 kilojoules, convert every 1 kilojoule to a joule. So that because at the end we will need to answer, or we will need to add up all of these. So what we have is 5.1 4.01 times 10 to the fourth joules. All right, so let's put a box around that. And that has taken us from here to here. Now that we have liquefied our sample, we need to heat that liquid to its boiling point, right? So we now need to take the pot of liquid and we need to heat it. So we need to go from 0 degrees as a liquid to 100 degrees as a liquid. So that's Q equals MC delta T. Q equals the 150 grams. The specific heat of the liquid is 4.184 joules per gram degrees Celsius, and the change in temp here is 100 degrees Celsius. So 4.184 times 100 times 150 equals 6.28 times 10 to the fourth joules. Okay, let's go back up to our graph. Now we need to take that liquid and boil it, right? So we need to boil it. We need to use our delta H VAP. So we're going to go from our liquid at 100 degrees Celsius to a gas at 100 degrees Celsius. Q equals delta H VAP, because it's liquid to gas, times moles. Q equals 40.2 kilojoules per mole, to constant, times our number of moles, which we calculated up above as 8.32. All right, now let's do that 40.2 times 8.32, and that is 334 kilojoules, but we need joules. So let's go ahead and multiply that by 1,000, and that is 3.34 times 10 to the fifth joules. Okay, we are now at 100 degrees, but we need to be at 120 degrees. So we're going to take our 100 degrees Celsius gas and take it to 120 degrees Celsius, and it will still be a gas. So we are now right here in our curve. Let me get one more color here. We're going to go from here to here. All right, so we will have to say that Q is equal to MC delta T. Q is equal to a mass of our steam. It stays constant. The specific heat of our steam, and the change in temperature here, which is 20 degrees Celsius. Notice all of our Q values are positive because we are heating up. And I've got a Q equals, okay, 1.92 times 10 to the second joules. All right, so all of my Q values are positive because I'm heating up. And if I was cooling down, they would all be negative because that would be removing the heat, but everything else would stay the same. And in order to get my final answer, I need to add up my individual answers. So I need to take this 6.15 with an exponent of 3. I need to add it to this plus 6.28 with an exponent of 4. I need to add it to this, which is 3.34 times 10 to the fifth. And then I need to add it to this. And what I get is a final answer that says 4.03. Let me write that a little bit neater, guys. 4.03 times 10 to the fifth joules. That is the amount of energy that is required to take 120 grams of solid H2O, increase its temperature, melt it, boil it, evaporate it, increase the temp again to 120. We had to do each, oh, we've left one out. We need to add this guy right there, plus 5.0 times 10 to the fourth. So we actually have a different answer. But all I need to do is change this. So I failed to add a guy. Always worth going back up, right? Making sure you didn't make a mistake. So I've now added all of my individual steps together. Notice I could do this graph. I could ask you how much heat is required to melt. And if I did, you would only be concerned with, sorry, I'm just trying to find a different color. You would only be concerned with this. Maybe you need to just evaporate. Well, you'd only be concerned with this. Maybe you're just increasing the temperature of the liquid. Or maybe you need to get to the freezing point and then increase the temperature of the liquid, but you don't need to boil. So you can go from any step to any step, right? You don't necessarily go from the very bottom to the very top, but you have to apply these equations, right? Each fraction, each part of the line, each segment requires its own calculation. If it was a cooling curve, it would go down and all of the heat would be negative because your changes in temperatures would be negative. All right, great guys.